What we learned yesterday is that you can solve certain exponential equations algebraically, meaning on paper using symbols and numbers, getting exact values, as long as all of the powers in the exponential equation can be written using the same base. So for example, if you took a look at 5D with a little bit of thought, you can determine that 16 is the same as 2 times 2 times 2 times 2, which is 2 to the 4. Powers of 2, powers of the base 2 are things that you should become familiar with. 4, 8, 16, 32, 64, and on and on. And 32 is 2 to the 5. So we can rewrite the 16. I'm going to rewrite the whole equation. 16 raised to the exponent of 2k minus 3 is equal to 32 raised to the exponent of k plus 3. So the 16 becomes 2 raised to the 4, and that in turn is raised to the 2k minus 3. The 32 is 2 raised to the 5, which in turn is raised to the k plus 3. And then what you want to do is eventually work towards, in all of these problems, 2 raised to some quantity equals 2 raised to an apparently different quantity. I mean, they're going to be equal, but they will look different. And if you have 2 raised to a diamond equals 2 raised to a square, diamond and square must be equal by comparison. What we end up doing here is using, doesn't matter the letters we use, the power of a power rule, which says that when you have a power like x to the m and it's raised to an additional exponent, then we can combine the two exponents by multiplication. So this 2 to the 4 raised to the 2k minus 3 becomes 2 to the 4 times 2k minus 3. I suspect many of you, I don't know, would have written 8k minus 12 there, right out of the gate. Like not right at the very beginning, but at this point here that I'm at, you probably would have written 8k minus 12. And I don't know, I'm going to do it this way, 2 to the 5 times k plus 3. It's been a while since I've marked diploma exams. I don't think that would be an issue. But then again, I don't know. Sometimes they're a little quirky in their marking guides. And you are using a rule here that says you're multiplying the exponents. That multiplication is not being shown in this line. It's happening in your brain. So I would recommend writing this line. At this point in time, though, you can drop the bases. You can say it's 2 raised to one thing equals 2 raised to the other. So it's okay for you to say 8k minus 12 equals 5k plus 3. I'm pretty sure you don't have to write these two exponents. You don't have to write these two exponents, 5k plus 15, in factored form and then multiply it out. You can just multiply it out. So anyway, then you solve this. You get 3k equals 27 by my count. I subtract 5k from both sides. I add 12 to both sides. So I'm left with k is equal to 27 over 3, which is 9. And that's the gist of the lesson for solving exponential equations. Of course, if you do not have an opportunity to determine a common base, because there is no common base between 5 and 1.08 that's a natural number. Then you can use graphing technology, you can use trial and error, you can poke around in your tables to try to set up window settings, or just poke around in your tables to find an approximate solution. And then the last thing we did, and it's a pretty big deal, is we continued to apply this formula, but the examples we looked at were specifically for compound interest. And you need to be familiar with what annual means, semi-annual, quarterly, and monthly. I hope that rings a bell from yesterday in terms of what we learned. Can you take a look at your work, please? Does anybody have any questions you would like me to go over? Go ahead, Janessa.
12.
Number 12. So cobalt-60 has a half-life of approximately 5.3 years. So what we're saying in this course is you were expected to know that if the half-life is 5.3 years, and I'll get to why I'm using the letter P in a second. A means years. Okay, so the A that I've written on the board here, 5.3A, is not the same as the A in our general formula. But we've run into this issue again and again in every unit. Sometimes we have letters that are used more than once for different things. Okay? In this formula Janessa, P is the length of time it takes the multiplication to happen. And in exponential growth or decay, there's a repeated multiplication. If, to go to a different example, because half-life is a little awkward, if something is increasing by 10% regularly, then B is 1.10, because it's 100% plus 10%, which is 110%, and in decimal that's 1.10. But my point is, B is 1.10, that's what the population is being multiplied by regularly. So, you know, if it's multiplied by 1.105 times, all that means is in the equation you would have 1.10 raised to the 5. That's what makes it exponential. Okay? So what you were expected to know with half-life, I'm going to put half-life here, is that this is the length of time, this is the time for a multiplication of 0.5. So it's not that the population is going up by 10%. What's happening is the population is losing 50%. We have to know that half-life means the population gets cut in half regularly. So when we say that the half-life is 5.3 years, that means P is the length of time, 5.3 years, for the population to be reduced by a factor of a half, or reduced to 1/2 of what it was. In other words, B is 1/2, or 0.5, right? Now, the other issue here, so we've got our two parameters B and P written in brown. We also need the parameter A in this formula. And A is the initial amount. And this is a little tricky, and it's why this problem stands out. You're not told the initial amount. You're told that it's reduced to 1/512th of the original amount. So, you know what you could do is you could say that we're going to start off with 100% of it. And then figure out what 1/512th of 100% is. Okay, but let's go with this. You can pick any number you want here. So I'm going to say A is 100%. So my function becomes y equals 100 times 0.5 to the t over 5.3. And I don't know that I've mentioned this. I think I might have, but I could be mistaken. I think it's a bad idea to put in the parameters and one of the variables in the same step. I think you should put in the parameters and get an equation. So this is our equation relating the amount of cobalt-60 left to the time. Okay. Another way to put that is this is the equation relating the time elapsed to the amount of cobalt. So what we really want to do is figure out what 1/512th is as a percent. Or just take, how about this? Just take, if we start off with 100%, and we're left with 1/512th of that, let's just multiply this by 1/512. And this is the percent we have left. Less than a percent. This is not everybody, this is not 19.5%. It's 0.195%. So that means that we can put in here 0.195, and the problem, Janessa, becomes what is t? But trying to solve that algebraically is not a good idea. We're going to solve it graphically. Someplace down here, and it's not that far from the axis, it's really close, is this 0.195. We want to find out where these intersect. So to finish this off, we're going to put in for y1, 100 multiplied by 0.5 raised to, we do need to put the exponent in brackets because the exponent is it's not just one thing, it's not just x, it's x over 5.3. And then 0.1, well, I'm just going to put here 1 divided by 512 times 100. Which is that number, right? The 0.195. Were you puzzled because I had a decimal there? Okay, sorry about that. So 1/512 remaining means 1/512 of whatever we started off with. And of in math means multiply, so we take 1 over 512 times 100. Now I'm going to set up my window settings. I want to go, we'll talk about x in a second, but I want to go up to 100 so I can see that start point of the graph. Now, in order for me to figure out how far to go x-wise, I'm going to explore in my table like we did yesterday. I'm going to start at 0 and go up by 1. This will give me an idea when I go to my table of how many years it's going to take. Like I'm already at 17 years and I still have 9% left. And I want it to be less than 1%. So this is going to happen somewhere around the 45-year mark. It's actually 45 years. Exactly, but we'll confirm that. I'm going to set up my window settings horizontally to go from, I'll go 40 to 50. Whoops. Yeah, 40 to 50. Now I'm not going to see, I have a feeling what did I do here? I didn't enter this right, first of all. 3, window, (100) times 0.5 raised to the x over 5.3. You know what's happening here is this graph, I suspect, this graph is coming down closer and closer and closer to the x-axis. And I'm looking so far over here, I can't see the lines. Okay? But I'm willing to bet that they're there. Okay? I'm willing to bet that if I go, it's still graphing, if I go intersect, they're there, they're just so close to the x-axis I can't see them. So the answer is actually 47.7. It will be a relief when we finally learn, and we're going to start learning about logarithms today, when we finally learn how to use logarithms to solve an equation like this. And I hope you can appreciate that sometimes solving something graphically is fraught with bumps in the road because you have to work on those window settings. Solving it algebraically takes the guesswork out of it. All right, we are going to move on now. This is an introduction in Chapter 8 now. This unit covers Chapter 7 and 8. This is an introduction in Chapter 8 to logarithms and what they mean. And this lesson can be found on page 10 of your unit handout. There are two main things that we're learning in this lesson, and it's easy to mix them up. It's easy to confuse these two things. One is a comparison of two different types of functions, an exponential function and a logarithmic function, and they are different things. They're different. They're connected to each other, but they're not the same. The second thing we're going to be looking at is writing logarithmic expressions as exponential and vice versa. That means you're going to take a logarithmic expression and write it as an exponential expression, and those two expressions mean the same thing. They're the same. It's like saying hello and bonjour. It's just in a different language. But when you talk about what I've highlighted in blue, those two things are not the same. They're connected to each other, but they're not the same. When you talk about what I've highlighted in green, those two things mean exactly the same thing, just translated into a different language. And we're going to be using our understanding of logarithms to evaluate logarithmic expressions. To begin with, what a logarithmic function is the inverse of an exponential function, okay? By definition, that's what it is. So to review inverses, when you find an inverse, if you have an equation of a function and you want to find the inverse, you take the x and the y and you switch them in the equation. This is from Unit 1. So for example, and this is not in your notes, but if I had this linear function y equals 2x minus 6, and I said, what is the inverse? That will be the inverse. Okay? These are inverses of each other. They're not the same thing. If you graph each of them, they look different. They mean different things. However, we do not like x equals. We would much rather have an inverse written in terms of y, not in terms of y, written as y equals in terms of x. So rearranging this is something you learn in, I don't know if you would rearrange this as a function in grade 8 or 9, but you know the mathematics of rearranging this. You would add 6 to both sides and divide both sides by 2 and get y equals 1/2 x plus 3. And you can make a note here that both of these functions happen to be linear. When you take the inverse of a linear function, you get a linear function. Another example would be this function, y is equal to x squared. If I said, what is the inverse? It's this. So these are inverses. They're not the same. They're different. Now, if I say you have to rearrange that for y, prior to last year, you didn't know how to rearrange that for y. You thought you did. You thought you'd just take the square root of both sides. But some new notation was introduced to you, and the proper way to rearrange for y is to write that. And think back even further. Before you learned about square roots, and I wish I had knowledge of all of the curriculum from grade 1 up to here, but I don't. Imagine before you knew about square roots, and your teacher said, maybe you're in grade 3, I don't know. Your teacher said that some thing squared is equal to 9. And I'm not talking about plus or minus here. We're not going to mess with an elementary kid's head with plus or minus. And the grade 3 student has their timetables down pat, and they do happen to know what squared means. They do happen to know that it's some number times itself. And they go, it's 3, right? Would you agree? Okay. So then at some later grade, they're introduced to, how did you do that? What did you do to 9 to get 3? Well, somebody in the history of math invented a symbol to describe what we're doing. And the invention of the symbol is this, right? But that symbol is something new. It's a new mark on paper that you hadn't seen before prior to seeing it for the first time. So keep that in mind, because when we get to exponential and its inverse, we need to introduce a new way to write what we mean. By the way, this is a quadratic function, this is a square root function. So if we take a look at this exponential function, we started off by saying at the top of the page, a logarithmic function is the inverse of an exponential function. Y equals 2 to the x is an exponential function. If I switch x and y, I get the logarithmic function. These are different. Okay? So if I were to graph y equals 2 to the x, it would look like something. If I were to graph x equals 2 to the y, it would look like something. But we call this function on the left exponential and the one on the right logarithmic. And they're different. The issue now is if I said to you right now, rearrange this equation on the right for y, you don't know how to do it. It's not a matter of multiplying by something or dividing both sides by something or taking roots of something. It's a matter of introducing a new notation. And when you rearrange x equals 2 to the y, and this is in your notes, you don't have to write this down, it's written as y is equal to the base 2 logarithm of x. That's how it's written. Just like, everybody, x equals y squared is written as y equals plus or minus root x. It's a way to communicate the opposite operation or the inverse operation. So when we rearrange x equals 2 to the y, for y, we get y equals log base 2 of x, or the base 2 logarithm of x. And I want to talk about how that's written, first of all. The y, the word log, and the x are all on what I call the main line. The base is written as a subscript. And I want you to notice that the base in the exponential function and the base in the logarithmic function are the same. Okay? So the inverse of a base 2 exponential function will be a base 2 logarithmic function. Now we have to deal with the details. Since, and at the end of all this, if you don't understand all of the subtleties, that's okay. But this is a 30-level course, and I need to explain them. Since y equals log base whatever, c of x, came from y equals c raised to the x, this would be an exponential. And this is a logarithmic function. And these are inverses of each other. Then whatever rules we had for what c is allowed to be in the exponential have to be the same rules for what c is allowed to be in the logarithmic. And this goes back to our first lesson in this unit where we said that c must be a number greater than 0 and c cannot be equal to 1. Right? The base is a number between 0 and 1 or greater than 1. But it can't be 1, it can't be 0, and it can't be negative. So that takes care of this idea here. Why are we saying this is true for a logarithmic function? Because it had to have been true for the corresponding exponential function. Now, why is it that x must be greater than 0? This is huge in this unit. Why is it that this thing, x, needs to be positive? The answer is that if you were to take a look, I guess I'm going to explain this with an example. If you were to take a look at y equals log base 2 of 0, okay? If you were to take a look at that, you know what? I'm going to leave this statement that I've highlighted in yellow until we learn one more thing. I fear as though if I were to explain it now, I would cause more confusion. And if I explain it in about 10 minutes, it would be very simple. Okay? But for the time being, the argument of a logarithm cannot be 0 and it cannot be negative. That's important. Okay. Look, we got to get used to the fact that we can use different letters for the base. I like to use B, your textbook uses C. So graph both y equals 2 to the x and log base 2 of x on the same set of axes. Let's use, I'm going to use the brown for y equals 2 to the x. You should know that y equals 2 to the x is an exponential function with the x-axis being a horizontal asymptote and a y-intercept of 1. And you should know that every time x increases by 1, y gets multiplied by 2. This is that multiplication I was talking about earlier when I did that problem with Janessa. That the base is what the repeated multiplication is. You're multiplying by 2 repeatedly. And if I go over to 3, I multiply by 2 again. And because 8 is 2 to the 3, that explains why we go from 4 to 8, because you've got an extra exponent. I could, I suppose, go backwards and divide by 2. I think that's pushing the limit of what I can confidently draw, if you catch my drift. So we're going to draw this as well as we can. It doesn't have to be perfect. That is y is equal to 2 raised to the x. And now I'm going to graph the inverse of that. And what I will say to you right now is this picture you're looking at for y equals 2 to the x should be familiar to you. You should know that's what it looks like. And the resulting logarithmic function that's the inverse of this is something you need to know what it looks like. Okay? But my experience is after we're done, most students will not memorize the new graph. They will go through this process every time to get a visual of it. The first thing to note is that these are inverses, right? These two functions we're graphing are inverses. And that means that if the x-axis is a horizontal asymptote on the exponential function, the y-axis must be a vertical asymptote on the inverse, because x and y switch. If we take the coordinates of this point, which are 0, 1, and switch them, it becomes 1, 0. If we were to take the coordinates of this point, which is 1, 2, and switch it, it's going to become 2, 1. I'll write that over here. If we take 1, 2 and switch it, it's going to become 2, 1. If you need to write down the coordinates as you're doing this either now or later, feel free. If I take the coordinates here, which are 2, 4, and switch them, I get 4, 2. And I think you can kind of see where this is going. It's doing the opposite of what it was doing. What was happening with the exponential is when x went up by 1, y was doubled. Now when y goes up by 1, x is doubled. Similarly, we'll get a point in here. And the logarithmic function looks something like that. And I hope that everybody can appreciate that these are reflections in the line y equals x, which is further reinforcement that what we've done is right, because that's what inverses have to be. And this function is y is equal to log base 2 of x. So we can go ahead and write down all of the information. The equation of the asymptote for y equals 2 to the x is the x-axis. The y-intercept is at 1, 0. There is no x-intercept. The domain is any real number, and the range is y is greater than 0. And everything I've written in brown, I hope you can appreciate. We should know that. That's what we learned a few days ago. And, even if you didn't know that, you should be able to look at the brown graph and write it. But the goal is you don't need to look at the graph to know that about 2 to the x. When I start talking now about the logarithmic function, when I start talking about the logarithmic function, the equation of the asymptote is x equals 0. It's the opposite. You can look at the blue dotted line, it's at x equals 0. That's the opposite of y equals 0. The y-intercept, there is none. No, there isn't one. And you can either look at the graph and see there's no y-intercept, or you can look at the original function and see there's no x-intercept, so the inverse would have no y-intercept. The x-intercept is at 0, 1. The domain is x is greater than 0, and the range is y as any real number. Any questions with that example? Okay. So now, this statement at the top of the screen is huge. It's not going to be maybe that useful just yet, but the usefulness of it is going to creep in over time as we look at more examples. A logarithm is an exponent. I want to remind you that when you have an expression, that this whole thing is called a power, the triangle is the base, the thing up top is the exponent. So exponent means the thing that the base is raised to. So I'm telling you a logarithm is equal to an exponent. The exponential function, y equals c to the x, can be expressed as this. Now I want to be very clear about something here. These are not inverses. They mean the same thing. We're changing languages here. We're going from writing something with an exponent, pardon me, we're going from writing something with an exponent to writing something with a logarithm. And you're going to get very used to this, but I want you to notice that this logarithm, this is the logarithm. What is it equal to? It's equal to x. X is the exponent. When you look at the exponential form of it, x is the exponent. So your logarithm is always equal to the exponent. And I'm saying these are the same. And I'm also saying here that y equals log base c of x is the same as, well, let's just do this without looking up top at what I'm telling you. What's the exponent? Well, the exponent is the logarithm, which is y. That means this is going to contain the base to the y, and it's going to be equal to x. And you are going to get used to this, okay? Translating from one language to another. So I'm saying this is the same thing. If I were to say that, that's the same thing. If I were to say this, it's the same thing. I want us to look at the bottom one. We're changing from an exponential expression to a logarithmic one. They have the same base, right? I want you to notice that if you were going from the logarithmic, the thing that's by itself in the logarithmic is not the thing that's by itself in the exponential. The argument in the logarithmic becomes what's by itself in the exponential. the argument in the exponential becomes what's by itself in the logarithmic. So, convert each of the following from exponential form to logarithmic form. Well, this will be a base 4 logarithm. A base 4 logarithm. And the base 4 logarithm, the whole thing is equal to the exponent. So this will be equal to p, which means the argument of the logarithm is n. I want to point something out to you. What I have written on the left-hand side right now is meaningless. Log base 4 is as meaningless as writing square root or sine or plus. There's no argument to it. It only becomes useful when you load in an argument. In other words, you can't divide both sides by n. That n is part of the logarithm. If I were to take a look at this one, well, this will be a base 2 logarithm. It will be equal to the exponent. It will be of 1 over 32. So log base 2 of 1 over 32 is equal to negative 5. And I know that as we look at the introductory kind of examples here, your mind probably goes, so what? It's like somebody has invented just a different way to rewrite things. You will see uses to this. Log base 10 of 100 equals 2. Well, it's going to go from a logarithmic to an exponential. So we are going to have a base, an exponent, and some other thing. Well, this logarithm is equal to 2, so the exponent is 2. It's a base 10. The other thing is 100. And now I want to take this opportunity to explain what I mean when I say a logarithm is an exponent. If I said to you, what is that? That is the exponent to which you raise 10 to get 100. This logarithm is the exponent to which you raise the base to get what you're logarithming, which is not a word. Okay? Over here, sooner or later, you will get into this kind of pattern that you will say, well, x to the m is equal to k. And it's going to happen. It's not going to be the case that when you see this stuff, you have to think very long and hard about it. You only have to be told that bonjour is French for hello a couple of times before your brain twigs and your brain does all the heavy lifting for you. How's my pronunciation? Nobody speaks French? Then my pronunciation is perfect. Let's take a look at 4 log base b of 9 equals 16. You cannot convert this logarithmic expression to exponential until you have a logarithm, not 4 times a logarithm. So we need to divide both sides by 4, and we get log base b of 9 is equal to 4, which means b raised to the 4 is equal to 9. Any questions with A, B, or C? Determine each of the following values. So what is this log base b of 1? Well, I don't really like doing this. I think this is a crutch we can lean on to begin with, but sooner or later you're going to have to throw that crutch out. That A stands for answer. We want to know what that's equal to. And my advice to you is this. When you have a logarithmic expression, if you don't understand what it means, translate it to the other language that you're more familiar with. and vice versa. So when I write this in exponential form, I get that. And now I'm going to say, what is it that I would raise a base to get 1? The answer is 0. 0 is the exponent on a power that produces a value of 1. So this is equal to 0. However, that means log base b of 1 is 0. It's equal to 0, and I'm going to write the 0 here in a second. But I want you to ignore everything above this line and just think this way. To what do I raise b to get 1? 0. Very quick example here. If I said, what is log base 2 of 16? That's the exponent to which you raise 2 to get 16. It's 4. You don't need to write it in exponential form. Okay? Well, what is this? What is log base b of b? It's 1. That's right, Jesse. Because this is saying, to what do you raise the green b to get the blue b? And b to the 1 will give you b. C is C is either really easy or hard on the brain. How many of you know what log base b of b to the n is? What is it, Will? It's n. This is saying, to what do you raise? To what do you raise this green highlighted thing to get this? Well, you raise it to the n. And now I want to explain. Well, it's equal to n. Now I want to explain why you can't take the logarithm of a negative or the logarithm of 0. Remember when I highlighted something about the definitions of the argument in a logarithm? I said that and you can go back to this portion and add notes if you want, but I said in log base b of x, x must be greater than 0. And I don't know, in my notes, I might have used c. Doesn't matter. So if I were to say, what is log base 2 of 0, I am asking you, to what exponent do you raise 2 to get 0? I'm saying this. What number do I put up there to get 0? Well, 2 is a positive number, and 2 raised to any number is never going to give you 0. It will always give you a value greater than 0. What about negative? What if I said, what is log base 2 of negative 3? Well, you cannot raise 2, which is a positive base, to an exponent and get a negative. So the argument must be greater than 0. Let's keep going. What is log base 2 of 64? It is 6, I think. Why is it 6 if your and mine thinking are the same?
Because, sorry.
That's okay.
2 to the power of 5 is 32, and just multiply that by 2.
So you knew that 2 to the 5 was 32 because you happen to remember it. I did the exact same thing. I don't automatically know that 2 to the 6 is 64, but I do know 2 to the 5. So this is saying, to what exponent do you raise 2 to get 64, and it's 6. Again, I'm kind of putting the pressure on you because I don't want you to have to write this. You could. Then you would be doing the stuff we did yesterday and saying 64 is 2 to the 6. Oh, the exponents are equal. I think this is overkill. This is a lot of extra work when work doesn't need to be done. This one, on the other hand, is more complicated. But how many of you are confident you know what log base 6 of 1/36 is? Will? It is -2. Because 6 raised to the -2 And I see a bunch of you grabbing your calculators here. I mean, you can do that. I can't stop you from doing that, but let's just talk about the meaning of this. This means 1 over 6 squared, which is 1 over 36. If you wanted to set this up using that kind of crutch, then you would write 6 raised to a equals 1 over 36, and then you would write everything with a common base. But that's basically what Will did kind of by looking at it. Informally, he realized that the exponent must be -2. So this is equal to -2. Log base 8 of 2 is a very tricky one. But again, I'll ask the question, how many of you feel as though when you say, to what do you raise 8 to get 2, how many of you feel as though you know what the answer should be? Mariana, what do you think? A third. And, you know, for those of us in calculus class, we do a lot of work with fractional exponents. This is from grade 11 math, but you should understand that a third means cube root. So how could you determine that it's a third algebraically without thinking about cube roots? You would do this. Oh, common base is 2. This becomes 2 to the 3a equals 2 to the 1. So 3a is equal to 1. Oh, a is a third. There's an algebraic way to do it. When the base of a logarithm is not written, for example, log 8, it is understood to be a base 10. It's called the common logarithm. We work in a digital mathematical system. The word digit comes from the digits on your hands, and that's how we invented the number system. We have 10 digits, so we use base 10. We go 0 up to 9, and then we have to kick it over to another decimal or another placeholder. So this means log base 10 of 10,000. I would argue that everybody should know that's 4. Because 10,000 is 10 times 10 times 10 times 10, which is 10 to the 4. This is log base 10 of 1 over 1,000. Which will be -3, because 1 over 1,000 is 1 over 10 to the 3, which is 10 to the -3. And I'm going to show you a trick now. It's a really useful trick. It could have been used here with E. That if you have log base 6 of 1 over 36, it will be equal to -1 times log base 6 of 36. We are allowed to flip the argument over and multiply the logarithm by a negative. And would you agree that figuring out that this is -2 is hard on the brain? Harder on the brain than figuring out what log base 6 of 36 is? Log base 6 of 36 is 2 multiplied by that negative. Okay. And that means over here with this one, we could have said this is negative log base 10 of 1,000, and log base 10 of 1,000 is 3, so it's -3. All right, estimate each of the following. So what is log base 3 of 50? Well, it's the exponent to which you raise 3 to get 50. So what is 3 to the 2? It's 9. It's not 50, right? If it was 50, then the answer would be 2. What is 3 to the 3? It's 27. Oh, it's not 50. If it was 50, then this would be equal to 3. What is 3 to the 4? Well, it's 81. So what's happening here is the exponent of 3 is giving us a number that's smaller than 50. The exponent of 4 is giving us a number bigger than 50, which means that log base 3 of 50 is between 3 and 4. And that's the best estimate we can come up with. If you think trying to find numbers in a range of values that give a right exponential value is difficult, try it with logarithms. It's very awkward here. You can't just look at the 27 and 81 and go, okay, I think it's going to be halfway in between or something. It's complicated. How many of you have figured out how to do it on your calculator? Okay. I may show that to you guys right away, but I probably won't, because I shouldn't even have said anything, because now you guys are going to be hunting for it. I want you thinking about this on paper. As soon as it becomes algebraic and not numerical, your calculator is useless. Okay? What is log of 250? Well, this is log base 10 of 250. Well, 10 to the 2 is 100. 10 to the 3 is 1,000. Which means that log base 10 of 250 is between 2 and 3. Just a quick pause and a check. Am I going too fast? Okay. Now we're going to solve equations. These are very simple equations. What is x equal to? They're so simple that many of them can be done by just looking at the expression and understanding what it means. So hands up if you know what x is equal to in this equation. What is it, Thomas? It's 3. Because x is the exponent to which you raise the base of 3 to get 27. I hope everybody is on page with that, on the same page. However, in case you're not, if you don't understand what this means, you convert it to the other language, and then it becomes more obvious. I really don't believe, though, that at this point in time, if you have to do this, I don't believe that you should have to do this, and then the light goes on. Oh, x is 3. I don't think you should have to write that, and say, I'm going to drop the bases. Log base 27 of 3 equals x. One that maybe you have to rewrite in exponential form, but by a show of hands, how many of you know what x is equal to? What is it, Lynette? 1/3. And can you explain your reasoning, please?
Okay, I just because 20 the opposite is.
So you've recognized a rule, right? And I'm going to give you another little trick here in a second. You've recognized there was something similar. Maybe you were thinking of log base 8 of 2, and it was 1/3. Or are you thinking that if those numbers were in the opposite places, it would be 3? That's the little trick I'm going to show you. This is 1/3. Log base 27 of 3 is 1/3. Let me write this out first, though, before I get to the trick. We would write 27 to the x equals 3. You would write 3 to the 3x equals 3 to the 1, so 3x equals 1. Lynette has stumbled across a very useful little rule, if you can remember it, that if I have log base a of b, it's equal to the reciprocal of log base b of a. So if I have a hard time thinking here, and what makes this question at the top of the page complicated in your brain is the base is bigger than what you want to get. But if I were to switch those two and say, what is log base 3 of 27? You know that's 3, I hope. Well, that means log base 3 of 27 is the reciprocal of 3. I guess I could have written this. Thomas. 3. Why is it 3? 3 to the power of 4 is 81. Excellent. So if you were to go x raised to the 4 equals 81, and just solve this not as a polynomial equation, not by factoring, not by doing anything else, saying what number do I raise to the 4 to get 81? It's 3. Or you could say, this will be important for later in the unit, that x will be the 4th root of 81, which is 3. Well, just a second though. A 4th root can be positive or negative. Right? Would you agree that's true? And that's true? So do we put plus or minus? No, why not? X is the base. The base must be greater than 0. Log base 5 of x equals 3. Hopefully when you see that, you're simply saying, well, what does it mean in exponential form? Who can tell me what x is? Kai? 125. Because this is saying 5 raised to an exponent of 3 gives you x, so that's 125. There's no single type of question we're dealing with here. It's all about taking a logarithmic expression and thinking of it in exponential form or vice versa. Log base 1/2 of 32.
-5.
-5, good. Now I'm going to solve this in a number of ways and then give you a third trick. Okay, so there are these extra tips that are not on your formula sheet, but if you can remember them, make things useful. When you did this, did you just say that 1/2 to the -5 is 3? There's 32? You just saw a pattern, kind of like what Lynette saw? Okay. If you were to solve this exponential equation algebraically, you would say 2 is 2 to the -1, and it's raised to the x. 32 is 2 to the 5. That means negative x equals 5, so x equals -5. Now, is this the last question? Okay. So what I told you earlier, I want to find it just to trigger your memory to make sure we're talking about the same thing, was if you take the argument and you flip it over, then it's the same as the negative of the logarithm. Okay. So one of the little extra rules I've given you is that if I have log base b of, say, 1/a, it's the same as log base b of a if you multiply it by a -1. The same is true if you flip the argument over. The same is true if you flip the base over. If I have log base 1/b of a, it's equal to log base b of a multiplied by -1. So any time you flip the base over or the argument over, you just multiply the logarithm by -1, which is a very useful thing to remember, because if I said, what is log base 1/3 of 1/81, it's 4. Because if I flip the base over, I have to multiply by a negative. And if I flip the argument over, I have to multiply by a negative. So if I flip both over, it stays the same. Don't confuse these two little rules I have at the top of the page here with A third rule, I said if you have log base a of b equals the reciprocal of log base b of a. That's another rule. That's if you swap the argument and the base, you take the reciprocal. I don't think this is something you set out to memorize, okay? It happens. That's the lesson. Don't confuse what is on the screen here with what is on the screen here. What is on the screen here is a comparison of two different things, an exponential function and its inverse, which we call a logarithmic function. It can be base 2 or base 3 or base anything. What we have here is a translation of one thing into the same thing, just with a different appearance. And that's the introduction to logarithms. So there's a variety of questions that you can practice here. By the way, I think on this handout, there's a boatload of extra pages at the end. There is always lots of extra practice with logarithms. Okay, tomorrow, we will look at transformations of logarithmic functions, and then we're going to start looking at the real application. So get to work, please.